Alright, guys, let's get started. So far, so in the last 2 weeks, we have covered HTML, CSS, JavaScript, jQuery, and then in the last week, we were focusing on databases and data persistent. We studied SQL, specifically the Microsoft SQL Server. Then in the NoSQL category, we studied the CouchDB, which is a document database. We studied Redis, which is a key value pair database. And then we saw the Azure table and the graph database Neo4j. In this week and the coming week, we are going to focus on C#.NET. And to start with that topic, we are going to build a quick background of microprocessors. So before before we get to that point, let's talk about digital electronics. Let's talk about digital electronics, right? Just 1 second.
Sir, you're not audible.
Can you guys hear me now?
Yes, sir.
Okay. I'm sorry about that. There's something wrong with my computer today. Uh, all right. So what I said so far is that the current that we receive at our place is this sine wave, which is at 50 hertz, and there is a device called the diode. And then the diode, if you given electric, give a sine wave to it, it removes the negative part. So um, this part of the wave is going to go away, will be eaten away, and then it will only output the positive part. Now, this is the beginning of digital electronics. Using these devices, we generate a series of ones and zeros. So if we put it through complex circuitry of diode and capacitors, uh, we are going to we can convert it to a more stable digital signal. And in these digital signals, they are a little easier to work when it comes to computers. So uh, when we say that, uh, okay, so this is like first part of digital electronics that we should understand. The second part is something called is the number system. So the number system that we are used to is called the decimal number system. Now, in a decimal number system, we have um, 10 unique numbers. So starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then after 9, we start we switch to the second number, and then we repeat this entire series from 0 to 9 right next to it. So after 9, it's going to be, say, 10 and 11 and 12, right? The number of unique digits inside a system is called a radix. So radix of a binary system is 10, right? Similarly, um, when we are dealing with computers, we use a system called binary, and binary had a radix of 2. So there are only two unique numbers in the system. The first is 0 and the second is 1. And after 1, we'll have to go in a repeating mode, and we'll have to start with 1 and then repeat the series of 0, 1 right next to this number. So the third number in the series is going to be 10. The next is going to be 11. And then because we have exhausted all the options, we'll have to switch to a 3-digit number system. So the next number in line is going to be 100, and then 101, and then 110, and then 111. This way, if we continue, what we get is decimal and binary equivalent of these numbers. Now, if you've seen a petrol meter or a counter at the gas stations, you will realize that when you reach the end, like this bit flips back to 0, and the next bit kind of turns to 1, right? So the same thing happens in binary as well, that when you exhaust the number of unique digits, you add there is another digit that you add to the left of this. So if I have to write represent it in 4-digit number format, I can put zeros to the left, and then that won't change anything. And then these numbers change to this format. Another 0 here and another 0. And then after this 3-digit number series is exhausted, we'll have to bump to the 4th digit. And then the next number is going to work out something like this. Now, the reason I'm explaining this number system to you is because it has a very close correlation to um, how computer programming works. And then, so this is the end of the 4-digit series of binary numbers. So if I complete the series on this side as well, we're going to see 13, 14, 15, and yep. So 0 to 15 is going to match very closely to this particular sequence here. Right? But then these are not the only number systems. There are at least 2 more popular number systems as well. So I'm going to leave. So the radix of this number system is 7, and it is called the octal number system. I'm so sorry. The radix of this number system is 8, and it is called the octal number system. So octal is going to have 8 unique digits. And if I can draw it right next to this series, it is going to look like this. So we're going to start with 0 once again, and then 1, 2, 3, 4, 5, 6, 7. There's not going to be an 8 here because we have we have consumed like all 8 unique digits. And then the next number in the series is going to be 10. And then 11, 12, 13, 14, 15, 16, and 17 as well. So octal 17 is equivalent to decimal 15 and binary 1111. We are not going to call it 1111. It is 1111. And then the last number system that we're going to study is the hexadecimal number system. And the radix of hexadecimal number system is 16. So it is hexadecimal. And then the unique digits of this number system, they are going to look like this. So we're going to start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then after 9, because we have not reached the count of 16, there are only 10. We switch to letters and A, B, C, D, E, and F. So this is the 16 unique digits number system, which is hexadecimal. Now, the reason we are studying this is because this is how computer stores information. When we want to save information to computer, it is very difficult to save a sine wave, right? Because sine wave, every unit of time, it is going to have a different value, and storing that thing in a hard disk or persisting it in any form of memory for that matter, like RAM or hard drive, it is going to be extremely difficult. Um, it is easier to store ones and zeros, and that's why we convert information in the form of 1 and 0, or probably if I can draw it again over here, it is another series of ones and zeros, right? So storing ones and zeros in the form of uh, in the form of magnetic current or magnetic polarity, it is going to be easier to store it in the hard drive. And that's when we switch from decimal to binary. And then this is a format in which information in computer is going to get stored. But then each number system has a unique set of operations in it. And in decimal, we are going to have operations like multiply and divide, addition, subtraction, multiplication, division. So because we are storing information in the form of binary, we would want to have some form of arithmetic operation, some form of arithmetic operation support in binary as well. So before we do that, let me show you a quick trick using which we can find out how to calculate bigger numbers. So if I give you a 3-digit binary number or decimal number, what this number actually means is that it is 5 into 100 plus 3 into 10 plus 4 into 1, right? The way we arrived here is we do 5 into 10, and then I don't know how to write it here, so I'm going to just use pen. 5 into 10 raised to 2, right? And let me write that later. Plus 3 into 10 raised to 1 plus 4 into 10 raised to. All right, so it is 10 raised to 0 over here. It is 10 raised to 1 over here, and it is 10 raised to 2 over here. So the spot that we are at, we're going to start with a count of 0, then 1, then 2, and then we're going to raise this number to the radix of that number system. So because decimal is 10, it is 5 into 10 raised to 2 because it is a second spot, right? And then this thing is going to give us the actual value, which is 534. For binary number system, it is almost the same. So if I give you a binary number, say 1101, then if I have to calculate the actual value of that number, I'm going to say 1 into, and then I'm going to put 2 over here, and then I'm going to raise 2 to the power of something. Then it's going to be another 1 into 2 raised to the power of something. and then it is going to be a 0 into 2 raised to something once again, and then it is going to be 1 into 2 raised to something else, right? So let's go ahead, and because 2 is the radix, we're going to put 2 here, and then this is spot 0, 1, 2, 3. So I'm going to do a 3 here, 2 here, a 1 here, and a 0 here. Now let's go on and start multiplying these numbers. 2 raised to 3 is 8. So it is 8 plus 4 plus 0 plus 1, right? So it is 12 plus 1, 13. So this number actually is the binary equivalent of decimal 13. Now, one of the ways of representing value with the radix is you start putting them in parentheses, and you mention the radix of that number system over there. So if it is a binary number system, you're going to put 1101 and put a 2 in the bracket like this. So it's going to indicate that this value here is a binary value. Now we found out how to use the radix to calculate the actual value, and then how to convert these number system from one type to another. The reason we have the octal number system and the hexadecimal number system is because these number systems have one-to-one mapping with their binary equivalent, right? So what I mean by that is, if I want to convert 13 to say binary, I cannot directly do it. I'll have to do this kind of weighted addition, weighted multiplication with the digit, and add those up to reach a value. But then in hexadecimal, it becomes extremely straightforward, because the series, it kind of runs parallel to each other. So if I have to put a next digit after F in hexadecimal, it is going to be 1 and followed by 0. Now, if I start representing all the hexadecimal digits with 4-digit binary equivalent, the number 10 actually becomes the binary equivalent of this thing. So we know that 1 is 3 zeros followed by a 1, and then 0 is 4 zeros. And then if we look at 1 and 0, it is exactly this, right? So 3 zeros followed by a 1, and then 4 zeros over here. When we do this, we can take any hexadecimal number and we can directly find out its binary equivalent. So writing binary gets extremely complicated. And as we are working on operating system level programs, they are going to become, it is going to be a lot easy for us to use the hexadecimal notation, right? So this is how you convert from one number system to another. Hexadecimal is extremely straightforward because the 16 digits map to 4 bits, which is also called a nibble, and conversion between binary and hexadecimal is straightforward. It is the same case with octal number system as well. So instead of the only change is that instead of 7 all 4 binary bits, you're going to use only 3 binary bits. So if I give you an octal number, say 17, 7, if I have to represent 1 in 3 digits, so it's going to be 0, 0, and 1, and then 7 as 3 digits once again, so it is 1, 1, 1, 1. And then if you look at 17 equivalent here, it is series of 4 ones together, and then zeros on the left does not actually matter. So we can pick up any number and then represent it in 3 bits, and you're going to get the octal equivalent of that number like right away. So if you, and then the other way around is also possible. So if I take a long binary number like this, all I have to do is to go to hexadecimal. I have to divide this number into chunks of 4. And then what I get here is 1 and A and A. So look at A, and then A is 1010. So it is actually 1AA. And this is how you do conversion from decimal number system to binary, octal to binary, and hexadecimal to binary. Now, uh, let's talk about the arithmetics in the binary number. So arithmetics, and specifically, let's talk about the add operation. So if I have 2 binary numbers, 2 decimal numbers, 3 and 5, if I have to do the addition, the total is going to be 8, and then we can probably do it on math or the regular method. But then things get tricky, a little tricky, when we have a carryover. So if I have number 6 and number 9 here, the sum is going to be 15, but then 5 is going to be the first um, part of the solution of the addition, and 1 is going to be the carry bit. When we are in the binary number system, um, we are going to have a similar problem. So if we start with say 0001, and if I want to add 1010 to it, our addition operation is going to look a little different. So let me space these out so that they are easier to understand. All right. And we are going to do the add operation on binary numbers over here. So 1 plus 1, because 1 is like the end of that series, we'll have to generate a carry right away. So 1 plus 1 is going to be 10 because there is no 2 in binary, so I cannot definitely put a 2. So I'm going to put a 1 here, and I'm going to give a carry to this particular series. So now it is 0 plus 1, and this is going to be a 1, and then all right, I'm so sorry. So this is going to be a 0 here because 1 plus 1 is 10, right? Um, this is going to be a 0. We're going to get a carry of 1. It's going to 0 plus 1 is going to be 1. There's no carry, so this time it can be 0, and then this digit can also be 0. So what we fix this. Right, so this digit is going to be 1 and this will be 0. And then if you go back and look up the values, this is actually number 1, this is actually number 5, and if we apply the weighted average as well, this is going to be number 6. So binary addition are a little tricky, and to solve that problem, there are multiple small devices that have been created, and then they are called as logic gates. So let's talk about logic gates real quick. There are three type of gates that you're going to come across. The first is an easy one, a NOT gate. Second is the OR gate, and third is the AND gate. Now there's something called as truth table. A NOT gate is a single input device, and it is represented like this. So it is a little triangle, a circle at the end, and two lines. So the input is, I'm going to call it line A, and then the output is always a negation of whatever is on A. So the truth table is a representation of what happens when you give an input and what is the output that you're going to get. For a NOT gate, if you give the input as 0, it is going to flip the bit and it's going to switch it to a 1. And if you give it an input 1, it's going to give you an output of 0. Right? So this is the truth table of a NOT gate. Now, an OR gate is represented with something like this. And it is going to have two lines on it. And the representation of this, if I remember, is probably addition with a circle. I'm going to come back with this. The output is going to be A or B. And then let me go ahead and draw the truth table for this. So instead of one line, this time we're going to have two lines, line A and line B. And then now we're going to have four combinations of these values. So A is 0 and B is 0. The next combination is A is 1 and B. I'm so sorry. Let me go ahead and change the LSB first. The next combination is A is 1 and B is 0. And then the last combination is A is 1 and B is 1. So the OR gate says that when A and B both are 0, it is going to be 0. When A or B, any of those two are 1, the output is definitely going to be 1. So this is the truth table of an OR gate, where at least one of these two has to be true so that the output becomes true as well. And then AND gate is a little different. So AND gate is represented like this. So a straight line and a little elongated D sign. And then once again, it is going to have two lines, line A and line B. And then it says that the output of AND gate is going to be true. I think it is represented with A dot B. So the output is both the lines, they have to be 1 if you want an output of 1. Right? So these are three logic gates that are present in all the electronic devices, all the microprocessors, microcontrollers that you receive, that you work with. Right? So things become very interesting when we start putting these gates together and start implementing little electronic circuits. So let's go ahead and talk about a circuit that can do this addition operation for us. Right? If I have to create a circuit using the NOT gate, the OR gate, and the AND gate, which is going to do this addition for me, that circuit is going to take multiple lines and it's going to give us an output. But then notice that there are multiple combinations that we have. Our line A and line B, they can have both values 0, and when they both have a value of 0, the output is going to be 0. All right, this is fine. When the input A is 0 and B is 1, the output is going to be 1. When both the inputs are 1, the output is 0. So let's go ahead and start comparing this addition operation with what gate we can pick up from this series so that we can match the output from this particular series here. All right, and so the first input is when both are 1, the output is 0. And then I don't see any gate here that is doing that is giving us that kind of output. So when both are 1, output is 0 is not present anywhere. When both are 0, the output is 0. When any of these two are 0, the output is 0 for the AND gate. When anything is 1, the output is 1 for the OR gate. So it kind of doesn't match over here. And then that makes me introduce to you another gate, which is called the XOR gate. Now, an XOR gate looks almost like an AND gate, an OR gate. I'm so sorry, an OR gate, and it has an extra line on the left side. So it's going to be an OR, right? And I think the circle on the plus sign is for XOR. So it's going to be A and then XOR and then B over here. Let's go ahead and draw the truth table of the XOR gate. So the XOR gate takes once again two inputs and the output is a little different. So what it says is when both the inputs are same, the output is going to be 0. And when they are different, the output is going to be 1. All right. So the XOR gate, it combines the NOT gate, the OR gate, and the AND gate in a specific combination. And then it makes sure that when both the digits are matching, the output is going to be 0. And when the digits are different, the output is going to be 1. Now, with this fourth member added to the family, go ahead and pull it closer. Right. With this fourth member added to the family, I think we can now go ahead and draw our full adder circuit using these four logic gates. Notice that we don't get like one line of output, we get two line of output. So let's start naming them. This is definitely the carry bit, and we're going to call it the sum bit. So when you add two numbers, say number A and number B, you're going to get two outputs. One is the sum bit and one is the carry bit. Now with this, let's go ahead and define what happens to sum. When you do a sum of 0 and 0, you're going to get a 0, right? So for a 0 and 0, you're going to get 0. So let's write sum over here, and probably I can do better if I start typing instead of this. Put a sum here. Right, this is line A, this is line B, and the output we're going to call sum. So I'm not going to put output here. I'm going to say sum. And if the output of if A and B both are 0, sum is definitely 0. When A or B is 1, the sum is 1. 0. Sum is going to be 1 once again. And then when it is 1 and 1, the sum is going to be 0, because this 1 and 1 is this column over here, right? So when we added 1 and 1, we got 10, but then 10 has a sum bit of 0 and carry bit of 1, correct? And then now if you compare this output to one of these 4 outputs, you're going to see that the sum bit is actually the output of the XOR gate. Make sense? Let's go ahead and see what carry does. So carry is going to be 1 when they are both 1, and carry is going to be 0 when any bit is 0, and it is this output here. So they both have to be 1 for carry to be 1. If anything is 0 in this entire series, it is going to be 0. So this output is what we need for the carry bit. So I'm going to change this output to carry, and then let's start putting these devices together. So I'm going to try and draw something neat this time. So we're going to definitely have 2 lines of input. One is line A, one is line B, which is going to represent these 2 columns on the left. And then we are going to need an AND gate, and we're going to need an XOR gate. Now let's go ahead and connect these things up. So A input goes to this, B input goes to this, and A input goes to this, and B input goes to this device here. And then if we can name these devices, this is going to be the carry output, and this is going to be the sum output. Right now, because we are processing like 1 bit of operation, it is calculating these values for us. This little device here that we are looking at is called an adder. Right, and let me go ahead and pull up a value. Let me go ahead and pull up a diagram from the internet. Then this device is called an adder. Now, the way we are going to see these outputs is we are not going to have these AND gates and OR gates available to us. What we're going to do instead is let me pick up an IC diagram. Integrated chip. All right, so there is a chip available in the market, probably number 7400, which is NAND gate. 7402 is for the NOR gate. I'm looking for other chips actually. Let me go search for a few images. And then these are some of the chips available in the market. So notice that this is the AND gate, and in front of that, there's a little NOT gate. So it is going to be exact opposite of the AND gate. I am looking for other chips as well. So this is once again NAND gate. This is NOR gate. This is the OR gate that we were talking about. And then those chips in reality, they're going to look a little like this. All right, when you say that this is input A, this is input B, for example, and this is the output. What we're going to do is we're going to take switches and we're going to connect those switches to these 2 pins. And then we're going to connect this pin to say an LED device. So when they are both 1, the output is going to be 1. If it's an AND gate, then if any of these 2 is 0, the output on this thing is going to be 0. Let me go ahead and look for a circuit. PCB LED. I'm looking for a different diagram. Yes, this is more like it. So we have done these exercise in our during our engineering days where we would be given this chip and then we're going to connect these wires. And I'm not sure if it is visible, but then there used to be switches as well. Okay, so these are the switches. If I press this, if it is pushed down, it would indicate an on. If they are popped out like this, the state they are in, it is going to be a zero switch, so an off switch. We have also seen those flip switches, like if you push it forward, it's going to be on. If it push it back, it's going to be off. And then you connect these things to the first two lines. So this is line A, this is line B, and then you take the third pin and you connect it to an LED. So depending on the combination of these switches, this LED is going to go on and off. Now, the reason I'm explaining you this is because the microprocessors that we see, right? They have billions and billions of those chips present inside them that are going to perform the operations that we run on our computer. So it is not going to be this ugly. There is an engineering technique. It's called VLSI, very large scale integration, where they make it like in a very, 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 very small size, and then they put it on these microchips, and there are like billions of those. Okay. Now, because we are taking only one bit of input, what we have created is a small computer, which is a 1-bit processor, and it only does the add operation. But then there are other operations as well, and like subtract. Now, subtraction of even decimal number gets a little tricky because subtraction can have a negative result. So 5 minus c is definitely 2. But then if I extend this example and if I do 3 and minus 5, the result is going to be minus 2. And because it is difficult to store sign bits inside binary, we are going to have difficulty when we perform this operation in the binary number system. So in binary number system, 5 is 101. If I put a 0 over here in 4 digits, it's going to be 0101. And then 3 is going to be 0011. If we subtract these two numbers, we're going to get 2. And I know that 2 is 0010. So this is what our result is going to look like. But then there is no way that we can represent a negative number in binary. So the solution that is proposed is if we have, say, 16-digit number, right? We are going to reserve the leftmost bit, this bit here, and we're going to call it the sign bit. If it is 0, it indicates a positive number. If it is 1, it indicates a negative number. So to the reason it is done this way is um, because there is a trick called complement, and then these complement, they actually indicate that if you have to add two numbers, it is going to be difficult. I'm so sorry. If you have to subtract two numbers, it is a difficult operation, but then addition is a simple operation. And then to come to the same result as so you would want 2 as the result, which is a difference between these two numbers. When you want to do that, you would perform the addition operation in such a way that you are going to get the result of 2. The trick for that is you find out what is the radix of that number system, and then you flip those two digits. So to subtract two decimal numbers, we're going to start here. We're going to take 5 and we're going to take minus 3. but then we don't want to do the subtract operation. We are going to do an addition operation. And then 3 is exactly 7 away from the radix of the number system, right? So we know that if we subtract 3 from 10, we're going to get 7. So we're going to say instead of subtracting 3 from 5, we are going to add 7 to number 5, right? And we're going to add these two numbers, and then we add 5 and 7. The result is 12. Now we say that we got the result, but we are going to delete the carry that we received, right? So we're just going to get rid of this, and we're going to say that this is our result. Now, this is true for all the numbers that, I mean, all the number system in the binary number system. So if I have to do 8 minus 4, this is tricky. So what I'm going to do is I'm going to do 8, and then I'm going to do an addition operation. And because 8 and 4 are 6 digits away, I'm so sorry, 10 and 4 are 6 digits away, we're going to do the addition of 8 and 6. The result is going to be 8 and 6 is once again 12. Right? So we're going to ignore this 1 over here, right? And 8 plus 8 minus, okay, what am I doing? Okay, 8 plus 6 is 14. I'm so sorry. Okay, and we're going to ignore 1, and that is our result. So because subtraction is difficult and not everybody gets it, everybody gets it, but because it's a difficult operation, what you do is you change the negative number to a positive number, and then you perform the addition operation. And the trick to that is you calculate the difference of this number from this number. Now in decimal, probably it looks a little difficult, but then in binary, it is called as ones complement. Now, what ones complement suggests is that if you have a 4-digit binary number, the ones complement, for ones complement, you will have to flip all the bits. So you change all the zeros to ones and all the zeros to ones. Right. So let's go ahead and try to subtract these two numbers again. So this is positive 5, this is negative 3. So I'm going to put a negative sign over here just so that it makes sense. And then what this number system or ones complement suggests is that you take the negative number and you flip all the bits. So I'm going to copy this here. I'm going to say that let's go ahead and flip the series. So it'll be 1 1 0 0. And now it says that go on adding these two numbers. So let's start here. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1, we know that is 10. So we're going to put a 0 here, and we're going to get a carry. So I'm going to write the carry over here. And then 1 plus 1, 1 plus this carry 1 here is going to be 10 again. So I'm going to put a 0 here, and I'm going to put a 1 over here. All right. So the result that we got in 4 digits is 001, which indicates that this result is wrong. But then because we have a carry, we're going to use this carry once again, and we're going to add it to the result that we got. And that way our result is going to be 0010, which is an equivalent of 2. So there's a 5 over here, and this is -3. And then when you add these two numbers, you're going to get a 10. The only problem with ones complement is that ones complement, if I have to represent 0 in 4 digits, is going to be 0000. But then -0 is going to have a different value. It's going to have 1111. And then based on our knowledge of maths, we know that 0 cannot have a sign. It is neither positive nor negative. And then this value here, it kind of presents a wrong picture. And then to fix that problem, there is another another binary system, which is called 2's complement. So what 2's complement says is You take ones complement first and you flip all the bits. So you change all the zeros to ones and ones to zeros. And then once you have the new number, you add a 1 to it. So if I add a 1 to all these, they're all going to switch to 0 because let's do it here. 1, 1, 1, 1. And then you add a 1 to it. So 1 plus 1 is 10. It's going to generate a carry. 1 plus 1 is 10. It's going to generate a carry again. 1 plus 1 is 0. It's going to generate a carry again. Another 0. And then 2's complement says that you ignore this carry bit here. Right? So it's going to be a 1 here, but then you ignore this. And the 2's complement of 0 is also all zeros. The advantage that we get through this is now if we perform the same operation, which is 5 minus 3, our data is going to look a little different. So 5 is once again 0, 1, 0, 1, and then negative 3 with 1's complement. Let me write that here. So it is 3 is 0, 0, 1, 1, and then 1's complement is 1, 1, 0, 0. Now if we add a 1 to it, it's going to become 1, 1, 0, and 1. So this is actually minus 3 up top here. And then this is the 1's complement, and this is the 2's complement. So let's go ahead and perform the subtraction operation on these two numbers. So 5 is 0, 1, 0, 1. And then we know that 2's complement of minus 3 is 1, 1, 0, 1. So I'm going to type 1, 1, 0, and 1. Right. Now let's go ahead and add these two numbers. Now 1 and 1 is 10. So we're going to put a 0 here and we're going to put a carry over here. And 0 plus 0 plus 1 is 1 and no carry this time. So it's 1 plus 1, once again a 0, and it's going to give a carry. And 1 plus 1 is 10 once again, and we're going to get another carry over here. Now, what it means is that in 2's complement system, when you get a carry, you simply ignore the carry. Right, and this is your result 0, 0, 1, 0, which is the equivalent of 2. So 2's complement is a better way of performing subtraction because you get the result right away, unlike in 1's complement where you generate an extra carry bit, a fifth bit, and then you got to process that fifth bit as well. Right. So we have seen two things. One, how to perform the addition operation, and then we found out that with the XOR gate, if we give two output, sum and carry, we are going to get a full adder. It's going to take 2 bits and it is going to give 2 bits of output. We also found out that subtraction is difficult and storing negative values in binary is also complicated. So we're going to reserve the left side bit as a sign bit. So let's go ahead and just to see an example of that, let's try subtracting 3 and 5. So I'm going to put the value of 3 over here, 0, 0, 1, 1, and we are subtracting 5 from here. So 5 is 0, 1, 0, 1. And if you want to subtract these values, the result is going to be negative. So let's go ahead, copy and paste. And what I'm going to do here is I'm going to take 1's and 2's complement of 5. So 1's complement is going to be I flip all the numbers. And 2's complement is that I add a 1 to this. Right. So this is 5 over here. This is 1's complement of 5, which is all the bits flipped. And then this is 2's complement of 5. Right. So let's go ahead and add this number to the value of 3. So 3 is 0, 0, 1, 1. And 2's complement of 5 is 1, 0, 1, 1. So I'm going to put 1, 0, 1, 1 over here like this. And let's go ahead and do the addition. So 1 plus 1 is 10. So I'm going to put a 0 here. And it's going to generate a carry. Now we have 3 ones, 1, 1, and 1. So if you sit long enough and try it, you're going to find out that it is 11. So it's going to give an output of 1, and it is going to give 1 carry. Now it is 0, 0, and 1. So it is going to be 1 here and no carry this time. And then this is going to be another 1, right? Now we know that this is a sign bit, right? If it's a 1, it indicates negative value. So this is our first negative result. Because we are subtracting 3 minus 5, we are going to get a result of -2. But then the first indicator of a negative operation is that we are not going to have a carry on the left, and this LSB bit here is going to be 1. When there is no carry, the result is definitely negative, right? Because we were expecting, we know that 2 is 0, 0, 1, 0. We were expecting that to be output, but then that didn't happen. Instead, we got 1, 1, 1, and 0. And then that is because this is 2's complement. If we take 2's complement of this once again, we are going to get back to our original result. So let's go ahead and do that. So 2's complement is you flip all the bits. So 1 changes to 0, 1 changes to 0, 0 changes to 1, and then you add a 1 to it. And then when you add a 1, it becomes on these two numbers, this becomes 0 and then generates a carry. All right. And then if you look at this, this is the value of 2. So 2's complement, you can subtract a smaller number, a bigger number from a smaller number, and the result that you get, if you take 2's complement once again, it is going to give you the actual magnitude of that value, and the result you would understand is a negative number itself. All right. The reason I'm showing you all this is because these adders and subtractors, they eventually are put together and into multiple bits. Right? These adders and subtractors, they are put together and they become part of microprocessor. There is a special unit inside microprocessor, and then that unit is called as ALU, the arithmetic and logic unit. So this arithmetic logic unit is going to have multiple such adders available inside this small unit, and it is going to do all the math operation that your computers are supposed to do. And then so far we had been looking at like only one bit, like A bit and B bit, but then the ALU is going to take significantly larger numbers. So if it is taking 4 bits, it's going to become a 4-bit processor. And it is not only going to take 1 line, it is going to take 2 lines. And the second line is going to be the B series. So B0 to B3 is 4 line, B0, B1, B2, B3, and A0 to A3 is once again 4 lines. And then this small piece here is the 4-bit binary address subtractor, or the binary arithmetic logic unit. This is a small component of a microprocessor. And then the microprocessor that we're going to talk about today is the 8086 processor. So it is already 9 o'clock. Let's take a quick break, and then we're going to come back in exactly 5 minutes. Okay, we're going to start sharp at 9:11. All right, so I'll see you then. Thank you.